this is the assignment brief. By the way, so besides that, so Kevin just before the lecture sent me a message that he gave some example and he had some amendment on that. So anyone wanting to look at that, look at the amendment he put in the comments there. So the assignment. So this is dot and boxes. So to get started, there's one thing you need to do first. And that is to basically add this intent filter to your activity. This will make it a launcher activity. There's plenty of documentation of how to do this if you want to.
Yeah, I saw the video.
Yeah. So it's just one of those things. So don't forget that. Of course, you can also, when you go to new, you can just create an activity. Say if you want a basic activity, we can then basically do something like, okay, press this launcher activity button. Okay, so that's how that works. There's a quick check. Something is using a lot of CPU on my system. So, okay, no, it's getting better. I think it was just running the thing there. So if you press launcher activity, that's what it does. So these features are quite important to know what it can do. You can even, by the way, also create a custom view. We haven't been using this because it creates a lot of boilerplate. Anyway, so So, by the way, if you want to add chat messages, you need to add them to the meeting chat, then I can still see them. So, or did I get? No, I'm not kicked out. So yes, it is the me. I can now see every meeting. So. Anyway, so that's the manifest, fairly simple. So what does it look like? So I added in these modules. So there is a number of these modules. So in the settings you can see which ones there are. So we have the app, lib, test lib, logic module, and the name of the project. You can change this to whatever you want, this project name. It's mainly used by IDEA to give this, give the title of the thing in the title bar, stuff like that. So, what are these modules? So, kind of the core module is the lib module. So, there is a README in Markdown. By the way, if you want to, there is a way to, so there is a plugin you can use to display this in a HTML way, but it's readable as is. So basically, this is where the base code lives. So when we look at this code, so we have a number of basic classes. We start, so we have this matrix class. We have done some exercises with that. But a matrix is just a 2D array, basically. So there's one for integers and one for general objects. So, and these are these interfaces. So yeah, there's a matrix common which has things, so I can press Ctrl B, and that will give me what the matrix common is. So it has a width and a height. We can ask what the indices of the columns are. We can ask the indices of the rows. And we have this function that we give a default implementation. So you can add default implementations and interfaces. That basically checks, is this a valid coordinate? And it just checks, is this within the width and within the height? the issue might be I didn't mute myself. I should be audible, but I might not be. So I disable audio from Teams. But no, you didn't mute me for everyone. Or you might have muted me on live stream, but I should have still have it on the team. So yes, so live stream is now no longer recording Teams. Anyway, let me know if you can't hear me. So we have width and height and indices valid, and we also create a function copy of, so we override this so it has this as a better return type. Okay, so then there's a sparse matrix that basically has a sparse matrix common, but basically it's the same functions. It doesn't have an implementation for its valid. So that is what matrices do. So there's these interfaces. So the main thing what they do is kind of, okay, this is the return type for this type. So that when you have a return type, you get the right thing back. So okay, it is actually a mutable sparse matrix, so we want to know that. So basically we have the non-mutable and the mutable ones, basically in line with the mutable list and list as used in Kotlin. So if you have a matrix that you don't want someone else to change, you only want to change it, so you can return it directly with the matrix interface. Of course, if people downcast, if people want to shoot themselves in the foot, they can. So let me have a quick look. That should help. Then we have so that's matrix basically, and then there's the implementations of this. So one of the things is it has an inline function. This is basically like that array thing I was talking about. So this inline function, it takes a width and a height, and then it takes an initializer. So we can create a mutable matrix. I didn't implement the read-only versions. I could have a matrix function that does this and then doesn't, just returns matrix rather than this, and I didn't bother with that. So basically there's one hack I need to do here, because I create the thing with an initial value. So I need to create one that accepts nulls with initial value, and then I fill those values, and then I cast it. So I know this is correct because I'm setting every value, but this is one of those cases where you're kind of doing a little bit, okay, I know better than the compiler can do it. So there's always limitations on the compiler. You want to limit that. So that is to create a mutable matrix. A mutable sparse matrix works the same, except it takes this validate function. It has a default value to just basically say, whatever you give me, it's always valid. So in this case, it functions exactly like a normal matrix, except that the validation is slightly less. And then there's a base class that does things, but let's skip this because we don't need to. One of the things that's interesting here is also the coordinate. So a coordinate is basically a pair. It is, but what this does, it's an inline class that stores this as basically two 16-bit values inside a 32-bit value. A little bit of a hack. but as far as you know, it just works like a pair. The important one here is this operator 1 and 2 that gets us these values in a XY thing, so you can use it in a nice gentle way. And you can use coordinates to actually access matrices as well as using X, Y. Anyway, so that's matrix. So for your assignment, we only need this one. So this is Dot and Boxes game. So it has an iterable of lines. So an iterable is anything that you can get an iterator of. Such a list would do. One of the things that matrix has, it is also iterable. You can get all the values in the matrix by the iterator. That's also what sparse matrix does, and that's why you want to say this position is not valid, because that allows you to basically use that. So that's kind of how that works. So then we have our players. This is just a list. We need to have a list of players for the testing. Boxes basically like lines. We have a current player. So we want to be able to know. So this is a value here. In your implementation, you would probably have this value have a private set function or a public one that you can actually set the player. So you can have a var that overrides a val. Important concept to realize. So we have the isFinished function. So, and in this case we have a default function to get the scores for each player. So it just creates us an int array for each player. So here's where we use also, for example. So this is the result. It's an int array, but we need to initialize it. But based upon the boxes. So this is I can't do an initializer here because it kind of works the other way around. We look at the boxes, and then for each box we just look at what's the owning player, and then we find out what the index of that player is, and then we set that to this. We could loop through everything twice and count only for this particular player. This loops every box only once, but then goes through the players to find out which one it is. But there's normally only 2 players, so that's a little bit faster. But it's arbitrary. In many ways it's arbitrary. There is the play computer turns. So this is called by the testing code when it says, okay, now a human has played, now make sure that the computer start the computer turns to play. So if the current player is a computer, you basically loop until either the game is finished or until you have a non-computer player. And the computer player, we come back to how that works. It's fairly simple in many ways. And there's these listeners that are there so that the game can capture those kind of things. So basically, let's see if we can do this. By the way, so if it's not clear, so the listeners are just there so that other bits of code are informed by your code. Significant here is this line interface. It's a nested interface, so it's part of the game. It doesn't really have an existence out of the game, so it doesn't really make sense to make it a top-level line because it has no use outside of this. So that's why it's a nested interface. Because in meaning, actually what it does is not different at all. It's only different in what it appears to do. So again, so a line has an x coordinate, x point, and a y point. We want to know whether or not it's drawn. So in the game you draw the lines. We need to, when we have a line, we want to know, is this one line drawn or not? And more important is you need to have the idea of how to so what are the boxes next to it. By the way, if you want to create a pair, you can just use the so get is null to null. So if you use the the to operator, that will create you a box. Obviously we don't want that actually in here because it's not actually valid here. We would always expect one box, but not always two, because sometimes there's one on the left, sometimes it's the leftmost line. So there's boxes next to it. This is where the coordinate system that I discussed, I think in lecture 2 or 3, is really important. You want to draw out how the coordinates work, or you can use the coordinates I put on my lecture slides. And we can then actually have the function. So actually making a move is through this draw line function. Draw line is, okay, draw this line. So yes, I put it on the line function rather than on the game, and then you pass it a line to draw. Which one is better is somewhat arbitrary. Again, we have a box interface. We basically have, it has a coordinate, x and a y, and it has an owner or not. This is a nullable player because by default it starts out as not having any owner. So nullable here is quite appropriate. And it has 4 lines around it. So in this case I just made it iterable, but it needs to be anything that has 4 values. Yeah, you could have a list of fixed 4 elements, but why do you want that? But those are the bounding lines. So basically the trick here is that and we'll go back into the more detailed implementation provided for you. But the big trick is that you need to have these box and line implementation to be able to access other lines or other boxes in the same game. And then there's these interfaces for the listeners, for the events basically we want to handle. So implementing this, let's quickly go to player. So we have, I think I discussed a little bit before, but we have this open play, the human player. So a human player is, let me see if I can zoom. No, that's not what I wanted. Now it's all compacted. Anyway, let's open it. I thought I'd see if I can zoom the font a little bit. I know how I can make this work better is by actually, this way you should be able to see it more, because it's actually going that way. So, okay. Anyway, so the human player is just a base class for any player, so it doesn't, as you can see, it has no method, no implementation. It's just, okay, I'm a human player. If you want to record a name, you create a child class that records a name, but it's not mandatory in this particular case. So when instead we want to so the computer player is basically also a player, so it's a player sealed class, so you have to be either human or computer player. Computer player has this make move function that you need to implement. So basically you get the game passed, you can record the game, the testing will work correctly as long as you only use that computer player with that particular game, you can record it and just ignore the parameter. So if you record state, that works. So this is a player. So then look at the abstract dot and boxes game. So this is a very basic base implementation you might want to use. So it is it basically provides the listener implementation. So we have the on game over and on game change, and we create a list to record those things, and we add them, and we add there. One thing here that we do notice is that it adds it always. So if you add it twice, you need to remove it twice. So this could be improved by doing something like if listener not in game over listeners that's the wrong one. Then we do this. So this is slightly more correct, and you can do that for on game change listeners too, obviously. So that is how that would work. Then we have the so there's these fire methods that basically allow you to make these methods. So that is just about events. So if you want a fire event, the easiest way is just call this. It's pretty obvious. So for every listener in the listeners, call this method. So that's how that works. Then we have an actual implementation of box and line. So an abstract box has a position, in this case that coordinate class that I talked about, and it is a box. So there is the position. There's also a constructor that just takes the x and y coordinates and then wraps them up in a coordinate. So if you want to use x and y, you can perfectly well do this with this class, even though it uses coordinates underwater. So it stores the position. So this is a property that it stores the position, and to get the x and y coordinates, it just has the getter for those two components. And abstract line basically does the same thing with lines, obviously. So one of the things you see here, by the way, is that coordinate actually has a generic parameter. So what is going on there with this generic parameter? So this generic, the coordinate does not actually store anything. So when we look at that, so there's this type parameter. So when we look at the implementation, we don't actually use it. So it's actually gray here to say we don't use it. The reason that this coordinate is there, that this type is there, is that basically we can then distinguish between this is a coordinate to a box, this is a coordinate to a line. These are not the same coordinates. So this is trying to use generic types with type erasure to make it work correctly, and to have the compiler help us with finding our errors. So if you look at this, that's what is going on. We have these kind of related types. They're coordinates, they work exactly the same way, but they point to different kind of things. So you cannot pass a coordinate to a line into something that gives you a box. So that's just a little bit of a helping hand if you want to use that. Okay, so that is basically the lib. So then in your logic, so this is where you provide your own implementation. So so the first thing is like this test thing. So you have this create game. So this is just there so that you can create your own classes. So the test class will it has all the tests, but I don't know what game implementation you have. So it hooks into this method where you can provide an implementation of your own game, basically, for a certain set of columns and rows and players. For that, be aware that the columns that it assumes are in boxes size, not in the amount of dots or in lines. They're in boxes. So a 3x3 game has 4x4 dots for all the outer bounds. So it is in the amount of boxes, not in the amount of dots. Yeah, so that's how I implemented it originally, and I only noticed this particular thing when I looked at it again. And the choice of which one you use is rather arbitrary, but you do want to kind of know that. So this is a more base implementation. So here it is saying use the matrix, use the sparse matrix. I also provided an implementation for this computer player turns. So what it does, so you don't actually need to do this yourself. By the way, you don't have to use student dots on box game. You don't even have to use abstract dots on box game. They are there to make your life easier if you find that useful. But this class you can change completely if you want to, or the abstract dots on box game as well. So, or make your own class instead. So what this one does, it's stores first locally what the current player is, and then we check, is this a computer player? It's perfectly valid here because we know it's either a human player or a computer player. It's a sealed class, and we haven't finished our game. That's important because we are not allowed to make moves if we are not finished. You don't need to look here about how is finished works. It actually isn't implemented here. It just has a to do. You need to implement that. So, but say we are a computer player and we're not finished, we call the make move method on the computer player with this game as a parameter, and then we go back and say, okay, what is now the current player? Okay, store that in the local variable. So yes, technically you could probably get away with directly accessing current player. I store it in local variable. So, and there's some slightly more implementation of this student line. So the important bit is inner. So basically this line has access to the inner class, so to the game. So if I want to get a box with a particular coordinate, I can just basically do something like return boxes, so 1, 1. Obviously 2 boxes 2, 1. So this is, if this was a horizontal line, this would work. Okay, okay, yes, boxes doesn't seem to be, yes. So student, so we return a student box here. So, and then it will work correctly, so I don't need to cast it because I know I'm actually only storing student boxes and stuff like that in there. So this is how you would work. Obviously these coordinates need to be different, but this is how it would work. The trick for you is to determine what are the coordinates given your current line coordinates. Again, the easiest way is to use pen and paper. Use that drawing. Okay, this is the box. Okay, how am I going to calculate the coordinate? If I know what the box is, what are the coordinates of the lines around it? If I have a line, if it's a horizontal line, what are the coordinates of the boxes next to it? If it's a vertical line, what are the coordinates of the boxes next to it? In the end, the math is actually really simple. It's just some divisions and some addition, but you do need to think about that carefully and looking at a picture of how it actually works with coordinates makes your life 20 times more easy. So draw a line here, in this case, if you just store lines, you can just record a property here where you draw the line. Then we have the box that basically works the same way. You can store the owning player. You can just use it. So what you can do is you can make it a var and just use it as a private set. So then it becomes a field, and you don't need to even do this. So this is a way of implementing that, but you then need to initialize it to null, obviously. So this is a way you could implement this. But there's many ways. You can store it or not. It's up to you what you want to do. So as you see, that it is valid to do that. So that's the student dots and box game. And so, why is it not? This is the name. Yes, it needs to be the local student box, isn't it? A student line. So yes, when you do it quickly, you get some issues. Anyway, so this is the logic. So then we have so the application is fairly simple. It's a dot. So you might want to get rid of the Android test. This is basically a test for Android. So this is just a sample generated one. I didn't do anything with it. I just left it there. So this one is just a main activity that just does something stupid. It has a button on it, and that's about it. So you need to replace this anyway, but just to have some starting point. One of the things that I'd like to also highlight for students is that there's no need to have the most latest system for your emulator. So when we look at the virtual machine manager, so I created a number of ones, but this one is, for example, an Android 7 one. You can even go back to much older version of Android. I think I did that. So what you can do is go here and say, okay, actually, I don't want Nougat. That is too much. I actually want to go back all the way to Jelly Bean. I want a Jelly Bean image. Yes, we don't need Google Play services in this particular thing. So if you have Jelly Bean, it looks a bit older, but it will work correctly. So we do this. Obviously, it will wipe it out, and then we can, and then you can start it. You can see that the size on disk becomes smaller. What you can do as well is in the advanced settings, you can actually give it more or less memory. So internal storage, etc. Okay, so yes, let me quickly fix this. Now you should be able to see it. So yes, sorry, it was capturing the window and I didn't realize that these dialogues were not a part of the window. So anyway, you can set your system image to something that's much older. As long as it is higher than your MinSDK level, it is fine. So yes, I fixed the in this case I can go to Jelly Bean, which is a kind of okay one. You kind of don't want to go earlier than that. So I have it on Jelly Bean. It's like in Nexus 4. We don't need that higher resolution, because frankly your computer will then scale it down so that it actually shows in your thing. So you can make it a single core CPU if you want to. You can reduce the RAM. stuff like that for people with less powerful machines. So then we can then start that, and let's see how it goes. It takes a while because okay, there it's coming up. It will take us a while because it's slow. Because it needs to completely do a factory reset because I changed the image type. Okay. So anyway, so that is something you might want to do for making your application development slightly easier if you have a less powerful machine. So I'm now running the application on that. So in the meantime, let's look at the testing library. So and this I can do with the other thing. So yeah, my Android Droid Cam crashed. So I put it on my laptop camera. You can see how that doesn't really work very well. What I can do is move it to this screen, and then you can see me a little bit better. So the testing library. So the testing library is just one class, basically, that provides all this test thing. Let's close the others. So there's some some base things. So here's the abstract create game function. So then there's a number of tests. So we can test what. So it tests first. So this is a parameterized test. So it takes a number of parameters. So from this method called game sizes. I will show you that later on. So basically that's a predefined set of game sizes that it tests with. So then it creates the game and it checks that all the boxes are basically within that coordinate. One of the game sizes it creates is a 1x1 game. If you use dots as coordinates, that will break because then you have 0 boxes. So it will also test the minimum width, that they're always the first is always 0. Does the same thing for my height, minimum and maximum. Okay, it should be almost to start the. It should almost have loaded the. So it has now loaded the sample implementation. You can see it just does this. So yes, so that's what happens. We don't really need to do much more. So let's get rid of. So then we have tests so for the lowest value for a line, that it is always 0 or higher. Horizontally, vertically, it tests that by default there are 2 players, because the create game function, if we look at that, it actually has a default parameter for players with 2 human players. So by default that should have 2 players. So in your implementation you don't need to provide that default, that's already done. You're not even allowed to override the default. And then it tests, okay, if we provide a player list, in this case we just create a random, so a different kind of players, 1, 2, 3 or 5 players. then it will create a game with those amount of players and checks that the amount of players is the same. So yes, you could do it with one player. I'm not sure whether it would be a fun thing. So one thing that this one tests is a little bit. One of the challenges sometimes is that you may have because we are working with references, it would be possible to change the original field, but then you pass it into the game, it just has a reference to the original list. So if you change this player list, get everything out, we don't want the players in the game to change. So what we want is the game to make a copy, for example, with the toList method. So you can have a list and then call toList, and then we'll just create a new list with those elements. So it tests that if we create a new game, then none of the lines is drawn initially. We test that none of the boxes are owned by anyone. We test that basically there are no duplicate coordinates in the lists, in the lines that we get. And then we test that, so this might have been called all lines have neighbors. Basically we tested all lines at least have one neighbor, because there's always a box to the left or to the right. So it's either one or two elements in the amount of boxes. So then we test that all boxes are a neighbor of a line. So what we do is we just get all boxes out of the game, and we get a sequence of this. So we do lazy transformation. We then make that into a coordinate, and then we store those coordinates into a set. So this is the functional approach to doing this. Yes, you could write this as a for loop, but actually this is a lot shorter. And then we have a set of boxes we've already seen. Then we go for every line. We're going to check that it is in the so we're going to look what are the boxes next to it. So yes, a pair is actually it. I made an iterable extension method that makes a pair iterable, ignoring all the null values. So to make this nice, because I do this a lot, and this is something you might want to do as well to make your code just easier to understand. So for each box in the adjacent boxes, we're going to say, okay, what's the coordinate? We test that it is in the expected boxes, because every box should be a neighbor. And we check that, we add it to the boxes we've seen. And then we check that at the end of the day, so we only add boxes that are actually in expected boxes to the list. And then we check that they are the same size. So this is how that works. The similar thing happens to test that all lines are around boxes. So you shouldn't have lines that are not surrounding a box. So if you implement this in a straightforward way, this is actually not that hard to achieve. So again, test that all the lines are unique. Again, it tries to store the things and do that. So test that all boxes are unique, so that we don't have duplicate boxes. So if we have lines and we have neighbors to a line, we check that for every line we check that all the neighbors are actually also a box. This might be duplicating some of the other code, but it works. One of the things we're also going to check is that if a box has if a line separates the boxes, so we can take box 1. If box 1 has a line, say to the right of it, that has box 2 and box 1 as neighbors. Then box 2 also has the line to the left to it with the same neighbors. So is that reflective? I mean, it should be the case. So you can't have discordance all over the place, basically. More straightforward one. Check that somehow the game throws an exception if you make a move twice. So here we can see the run function, for example. So it creates a box, so it creates a line. So it gets a random coordinate, so a random line for that. We draw the line and then we store the coordinates in line coordinates. Thanks to the contracts, this works. So the line is completely gone here. We only have the coordinates. For testing purposes, I don't want to store the line. I want to get a new line with those coordinates. So, and I know coordinate is correct, so that it doesn't actually contain a reference to the line, because that's not possible. So we get the line again in this block. We make sure that it is drawn, because it should have been drawn. Slightly off-topic test here. And then we draw the line. And we assert that this throws an exception. Any exception would be fine. I don't care what you throw. But if you try to draw a line, it's correct to throw an exception. Then we have the making a move. So basically tests that making a move works, so that draw a line works, that we can then have so the lines are the same, that basically tests all kinds of things, that the move is valid, basically, that all updates are there. This tests basically if I have a box and I draw all the lines around the box, that also sets the player. Again, simple game rules. I check that removing a game listener actually works. So I add the listener and then I play, and then I make sure that I basically have these test listeners that I can then interrogate. How often were you called and what were you called on, etc. So that's basically what this does. I also test that playing a full game by basically random playing all the lines completes the game. There's some hackery going on there, especially with computer players and with players, to allow them to share the same list. It's not really important how this works. This gets a bit, well, you can see it's a very long function that does quite a lot, but it plays an entire game. So it also, then we test that computer games actually work correctly. So computer players, so the only requirement for your computer player is that it plays a valid line. So what you could do is just find the first line that's not drawn and draw it. So you can use the game.lines.first and then put as a predicate is drawn as false or not is drawn, and then that's the line that you're going to play. That is the simplest computer player you can get. It's even simpler than doing a random, but random is basically, well, also almost as easy. So yeah, so this game basically, this checks basically if you have a computer player. So one of the things we need to do, if the first player is a computer player, we need to start this playing to happen. And then we say, okay, do we have still lines to play? Because this computer player actually picks it from the predetermined list of lines that I've used. So if a computer player, so basically make sure that we draw the lines, we check human things, and then we basically record, so check that the computer turns actually works, and that makes sure that basically the amount of turns the human has plus the amount of turns the computer has together are the same as the amount of lines. So this is these are the static things I talked to you about back, because like in all these functions they had parameters. So these are the game sizes I use. So I have a 1x1 game, a 1x5, 5x1, 5x5, 8x8 and 10x10. So game move data, so basically because I want my tests to be repeatable, I create a random object with a seed that I just hard code here to be basically 1, 2, 3, well, in hexadecimal 1, 2, 3, 4, 5, 6, 7, 8. So yeah, just from the perspective of having something repeatable. And then I have different sizes of moves, of boxes, and how many elements. Yes. So, and this is the amount of moves I put in there, etc. So, and this is so to get a core. So if we have an iterable of lines, so rather than using sparse matrix, because I wanted to not require you to use sparse matrix, this helper function actually allows me to get a line with the coordinate from an iterable. So what this does, it uses basically this optional casting. So it says if it's a sparse matrix, remember a matrix is also a sparse matrix, then I just get it by coordinate. If not, I'm just using this function to find the first element in the iterable that has that coordinate. So yes, if you use sparse matrix, the testing will be faster, because it can directly get to that coordinate rather than having to search for it. But don't worry, even searching 100 elements is really, really fast. And the same thing with boxes. And these need to be separate functions because box X and box Y are different. And this is the operator for pairs to get the list out of things. So yes, you can do this and then use it somewhere else. So basically say, okay, if there's no elements, that's an empty list. If we have one element, that's the list of if the first one is null, then it must be the second one. And yes, I use the bang bang here because I actually know that it's not null. But a pair technically could be changed because it's not. The implementation of pair could change so that it changes underwater. That doesn't happen, but that's why I need to use the double bang to say yes, it's not null. And so basically create a list. So and then I get an iterator of that list. That's the easiest way of I could do this. This is test code. Efficiency here is certainly not very important. Same thing with contains. So we want to make sure is this in this pair, if the first is the value, second is the pair. So pair is a very bare bones thing, but we can use extension methods to basically not require it. Same thing, like if we have a box, we want to compare, is it the same? So okay, so this takes a nullable receiver. So this means that our box, so you can call it with a null object and it will work correctly. So null values are only the same if both sides are null. Otherwise, it is. So I could. So when the order is not null, then so it's true if the order is not null and my coordinates are basically the same as the other ones. And the same for lines, straightforward. And we also have the a function called equivalent pairs of boxes. So basically, we consider a pair of boxes equivalent if they contain the same boxes, not whether the order is the same. The order doesn't matter in the testing. So that's why I have an equivalent function, because I don't want to write this code everywhere I want to use it. When I reason about are these boxes so do we get the right boxes and are they reflexive, I don't really want to know about how do I check that these boxes are equivalent. I use a separate function for that so that it just makes it much easier to understand the code, and I just have some separate function where I need to think about, okay, how do I do equivalence. So yes, so again, so getting a coordinate out of this. Again, this is a helper function to make that work in all cases, even if you do not use the abstract box with coordinates directly. Then I will just wrap one then and there. So this is the test computer player. So it records the amount of turns it has. You can provide it an iterator where it uses to get its moves, and then when it makes a move, it just picks the coordinate of the line coordinate that it needs to move next. It gets that line, it draws it, it checks that, because it's testing code, it checks that that line is now drawn, and it records that it made a turn. And then it, for all the boxes next to this line, it checks that if all the lines around it are drawn, then this computer player that just made the move is now the owner of that. Otherwise, if they're not all drawn, then there should not be an owner. So we assert that that value is null instead. So even the test computer player checks the correct ownerships, so to speak. The same thing with the test game listener. So it listens to both things. So when the event happens, so it just records how often the game change method was called, and checks that the game that we're being passed is the one that we expect to see. And the same thing on game over does basically the same, and it records that it has been called. And of course it checks that on game over is never called twice, because a game cannot be resurrected from the dead, so to speak. Okay, so that's the test code. I think so. We did app, we did logic, we did testlib. So that's basically the entire assignment.